All right. I believe we should be live now. So, um, welcome everyone. This is part two of our Math 2501 2601 linear algebra seminar, presented by me and Fred. So today, before we get into it, I guess here's an attendance form. So I'll give you guys around 20 seconds to fill out the form. It's very useful for us. So if you're watching it live now or just watching it later at yeah, please fill this out. All right. We'll go ahead and look at which topics we're overviewing today. So today, I'll be going through eigenvalues and eigenvectors, including applications and the singular value decomposition, which is for Math 2601 only. And then Fred will be taking the canonical Jordan forms and matrix exponentials slash ODEs for the second part. So today we're starting off by looking at eigenvalues and eigenvectors, okay? So it begins by taking a look at the definition. So if V is a vector space and T is a linear map on the vector space V, um, now an eigenvalue is the value of lambda such that T of V equals lambda V. So basically, if you plug a vector into the linear map, what you get is only a scalar multiple of that vector out. So the direction of the vector is not changed, but its length is scaled by this value lambda, which is called the eigenvalue. Now, the actual vector v is the corresponding eigenvector. Okay, now an important definition here is that the spectrum of T is the set of all eigenvalues. Okay? Okay, so in terms of eigenspaces, so an eigenspace would be the set of all eigenvectors corresponding to a certain eigenvalue. So for example, if we had an eigenvalue lambda, the eigenspace would be the set of all vectors such that T of v equals lambda v. Okay, now eigenspaces are invariant under the linear map. So if you remember from, I guess, the linear transformation part of this course, invariance means that um, if you put a subspace into a linear map, it remains a subspace of itself. Okay? So some basic properties here. Well, first of all, like the eigenvalues, like this is as we've previously defined. Now the eigenspace is given by this. So you can say that the eigenspace corresponding to a certain eigenvalue is the kernel of lambda I minus t. Okay, and that comes from actually taking, okay, t of v um, equals lambda v, okay, and actually solving this. So the question is, what are the values of, or what are the vectors v that satisfy this, okay? And those are the vectors given by the kernel of lambda I minus t, where I is the identity map. Eigenspaces are T invariant. So this makes sense given that if you take a vector, its direction is not changed. So if you took the eigenspace, it should be invariant under the linear map. Okay, so some other properties here are that if we have two distinct eigenvalues, so over here we have distinct eigenvalues, so they're different, okay, then the intersection of their eigenspaces is the zero vector only. Okay, so keep in mind here with the definition of eigenvectors, very important is that any eigenvector is not zero, because you can see if you plug zero into the linear map, you get zero out. Okay, so it's kind of a trivial eigenvector in that sense. So we're saying that all eigenvectors are non-zero. Okay, so this is saying that if we have two invariant I guess two distinct, eigenvalues, then their eigenspaces only intersect at the zero vector. So that's sort of the common eigenvector in that sense, is only the zero vector. So a matrix A is diagonalizable, okay, if and only if it has n linearly independent eigenvectors associated with it. So this comes into sort of why we bother with eigenvectors and eigenvalues. So it's because sort of using eigenvectors as a basis allows us to represent any linear map with the simplest possible matrix, and that's a diagonal matrix. And the reason why is because say I had an eigenbasis, okay, so I had an eigenbasis where I had v1 up to vn, and this is my set of basis vectors. And with respect to this basis, then the coordinate vector of v1, for example, would be 1, 0, 0, 0, etc., right? Now, we know that if I plug, let's say, v1 into the linear map, what I'll get is lambda 1 v1, okay, because it's an eigenvector, okay? Now, if that's the case, then if I have a representation of my linear map, I guess, with respect to the eigenbasis, then um, what that's going to be is just a diagonal matrix with the eigenvalues in the diagonal entries. And the reason why is because you can see that if I took my first eigenvector, which I'm representing as 1, 0, 0, 0, 0, what I'm going to get is just lambda 1, 0, 0, 0, which is precisely lambda 1 times v1. And same with lambda v2 and up to vn, right? So you can see that if I have some eigenbasis, which is a basis consisting of eigenvectors, then my linear map is just diagonal, represented with respect to that basis, okay? So what this is saying is that any matrix, right, can be represented or is similar. Okay, so you can see that this is the same as our definition for similar, is similar to a diagonal matrix. Okay, so if P inverse AP equals a diagonal matrix, it's diagonalizable. Okay, and what's that saying is that these vectors P inverse and P are there to change basis. So those are change of basis matrices that put us into our eigenbasis. So then the representation of the linear map will be a diagonal matrix. Okay, so here it says it's only diagonalizable if and only if it has n linearly independent eigenvectors. This is telling us that we have an eigenbasis, right? So this is an eigenbasis because if we're working in an n-dimensional vector space, then sorry, eigenbasis. So if we're working in an n-dimensional vector space, then if we have n linearly independent eigenvectors, then what we have is a basis of eigenvectors, and therefore we can diagonalize the matrix because its representation with respect to the eigenbasis will be a diagonal matrix. And we'll look at this idea of diagonalization in a bit more detail soon. But before we do that, let's look at another definition. This is multiplicity. Okay, so first of all, this is not exactly our definition of the characteristic polynomial in the notes. The characteristic polynomial is actually defined as lambda I minus a. Okay. Yes. So the point remains that to actually find eigenvalues, okay, how do we actually find them? What we can do is solve this, which is equivalent to solving, sorry, this should be CPA of t equals det a minus lambda I. Okay, so the reason why that's the case is because remember that for a particular value for lambda, so for a particular eigenvector, the eigenspace was equal to the kernel of a minus lambda I. Okay, so that's equivalent to saying, okay, a minus lambda I of v equals 0 for non-zero v. Okay, so that means that a minus lambda I can't be invertible, so we need its determinant to be non-zero. Oh, to be equal to 0, sorry. Okay, so actually solving for an eigenvalue is equivalent to solving this. Now, if you see, this determinant will actually give us a degree n polynomial. Okay, so essentially the eigenvalues of a matrix A are the solutions to this characteristic polynomial. So now the algebraic multiplicity of an eigenvalue is the multiplicity of the root in the characteristic polynomial. So for example, if the characteristic polynomial was t minus 1 squared, t minus 2, t plus 1 cubed, for example, okay? You can see that the multiplicity of 1 here is 2. the multiplicity of 2 is 1, and the multiplicity of -1 is 3. Okay, that's just looking at the power there. Now the geometric multiplicity is actually the dimension of the kernel of A minus lambda I. So this is the dimension of the eigenspace. So if you take a particular eigenvalue and you find the eigenspace and its dimension, then that's the geometric multiplicity. Now the geometric multiplicity is always less than or equal to the algebraic multiplicity. Okay? So for example here, with these algebraic multiplicities, one has an algebraic multiplicity of 2, but its actual geometric multiplicity may be less than 2. Okay? Depends on the particular scenario. All right. So we have a result here that says a matrix A is diagonalizable if and only if for every eigenvalue lambda I, we have the geometric multiplicity equals the algebraic multiplicity. Now, this is kind of telling us that given that its multiplicity in the characteristic polynomial is 2, then the actual eigenspace has dimension 2. So that means it has two linearly independent eigenvectors, okay? Now, the reason why is because you can see that if you look at our characteristic polynomial, right, the actual sum of the algebraic multiplicities will equal n. So if you add all the algebraic multiplicities, if you sum them all up, you'll get n. Okay, that's because it's a degree n polynomial. Okay? Now, the sum of the geometric multiplicities needs to equal n for it to be diagonalizable. And the reason why that is because for it to be diagonalizable, we need an eigenbasis, and therefore we need n linearly independent eigenvectors. And the only way to get n linearly independent eigenvectors is if all the geometric multiplicities are n, if you add them all together, and that'll tell us that we have n linearly independent eigenvectors. Okay, so we need for every eigenvalue for its geometric multiplicity to equal the algebraic multiplicity. Okay. All right, so we'll jump into an example now. So find the eigenvalues and eigenvectors of the following matrices. Find their corresponding algebraic and geometric multiplicities. So for these ones we're going to do, like for example, if I look at a 2 by 2 matrix, probably the quickest way of finding the eigenvalues and eigenvectors is to use the following result. That the trace of a matrix is the sum of the eigenvalues, and the determinant of a matrix is the product of the eigenvalues. Okay? So if I look at the first matrix, right, its trace, we'll call it A, is 1 plus 4 equals 5, and its determinant is 1 times 4 minus -1 times 2, okay? So what we get is the sum of the eigenvalues is 5, and the product of the eigenvalues is 6, okay? So we can look at this, and then by inspection, we see that the eigenvalues should be 2 and 3, okay? Now, once we find the eigenvalues, to find the eigenvectors, we actually need to find a sort of a basis for the eigenspaces. And what I mean by that is we need to investigate the kernel of A minus lambda I. Okay, so in particular, we need to look at the kernel of A minus 2i and the kernel of A minus 3i, and then we need to find basis for each. We need to find a basis for each. And now to do this, well, it's something that we've kind of seen before already, right? So if we look at E2, for example, okay, that's equal to this kernel, okay? Now if we look at this kernel, right, we're kind of solving for when, for which non-zero vectors make this equal to 0. And you can see that in this case, if you row reduced, right, you'd get -1 to 0, 0, okay? And so if we wanted to find a basis for this, we could say, okay, x2 equals like a certain constant. So x1, we could say, well, it doesn't really matter actually. So we'll say, okay, x2 equals lambda, and then so -x1 plus 2 lambda equals 0, and so x1 equals 2 lambda. And then what we get is the span of the vector 2, 1. Okay, so we can see that the actual eigenspace will be the span of 2, 1. All right, now we can do the same for the second one, which is lambda 2 equals 3. And then what we get is the span of 1, 1. Okay, so our first eigenvector would be 2, 1, and our second eigenvector would be 1, 1. So remember that eigenvectors are sort of not unique, okay? The eigenvalues are the important ones, and once we find them, we can find the eigenspaces, maybe with respect to the span of basis vectors. In this case, they're 2, 1, and 1, 1. Okay, so now we want to find the algebraic and geometric multiplicities. So you can see that in this case, right, we can see that the geometric multiplicities are both 1. Okay, now we know that the geometric multiplicity is less than or equal to the algebraic multiplicity. And further, if we add the algebraic multiplicities, we get 2. So in this case, each of the algebraic multiplicities will have to be 1 as well. Okay, and so they're 1 and 1 for the algebraic and geometric multiplicities for both respectively. All right, so let's move on to a 3 by 3 example. In this case, we'll actually find the characteristic polynomial. So in this case, it's actually fairly straightforward. We can find the determinant. So first of all, like we subtract t along the diagonal entries, and then we can find the determinant. This matrix is not too bad because you can see we have these zeros here that make it a bit easier for us. And so our characteristic polynomial would be this, right? Just keep in mind that, um, yeah, this is fine. So if we actually look at this, right, you can see that the solution for this equal to 0 would be t equals 2, 2, and 4, right? So you can see that what we have is 2. 2 has algebraic multiplicity of 2, and 4 has algebraic multiplicity of 1. Okay? Now we need to find the geometric multiplicities. So in that case, it's a matter of finding these kernels again. So if we look at 2, then we'll get the kernel of this matrix here. And we see that that's equal to the span of 1, 0, 0, and 0, 1, negative 1. Now we can do the same for 4, and that will give us the span of 0, 1, 1. So you can see that this has algebraic multiplicity 2, sorry, geometric, and this has geometric multiplicity of 1. Now in this case, the algebraic multiplicities were equal to the geometric multiplicities. Remember, that's not always the case, okay? There could be the case where we find that, 2 had an algebraic multiplicity of 2, but its geometric multiplicity was only 1. And in that case, the matrix would not be diagonalizable. Okay? Alright, so now we're looking at another example here. For each of the following matrices, use the additional given information to find the eigenvalues with their algebraic and geometric multiplicities without determining the characteristic polynomial. So if we look at this one, we're given 2 eigenvalues. Now we know that the trace of the matrix is the sum of the eigenvalues, right? So you can see that if we sum the eigenvalues here, we should get lambda 1 plus lambda 2 plus lambda 3 equals 2 plus 8 minus 7, okay? Which which equals 3, right? And if we take the actual 2 minus 3 plus lambda 3 equals 3, then what we get is 4. So the last eigenvalue is 4. Now, you can see that the algebraic multiplicity of each of the eigenvalues is 1. Okay. Now, in this case, we don't actually have to find, the question never asks for us to find the eigenvector. And now we can conclude that the geometric multiplicities should be 1 as well. Okay. Just based on the fact that we have our 3 eigenvalues here with arithmetic multiplicity of 1. Okay. Alright, so our second example was D, given that these two vectors are eigenvectors. Now, if we're given eigenvectors and we want to find the eigenvalue, it's not too difficult, right? Because we can just multiply the vectors in the matrices together and see what our eigenvalue is, right? So if we actually do it, right, we see that if we multiply the matrix and 1, 0, 1, we'll get 3, 0, 3. Okay, so the eigenvalue must be 3. And then similarly for the second one, the eigenvalue must be 1. Okay. Now again, now that we know the eigenvalues, to find the last eigenvalue, we just sum all the diagonal entries. That equals the sum of the eigenvalues, and we can find the last eigenvalue. Okay. So we'll move on to diagonalization, which we're going to look at in more detail now. Okay. So the following statements are all equivalent. T is diagonalizable. 2, there is a basis for V consisting of eigenvectors. So this is the eigenbasis that I was talking about earlier. Okay. 3, V is the direct sum of the eigenspaces of each of the eigenvalues. So what that is telling us is that V equals E lambda 1 T plus, that's the direct sum, so forth up to the nth, it doesn't really matter what the nth, we'll just say in this case, the nth eigenspace, right? Keep in mind that it doesn't need, if it's an n-dimensional vector space, it doesn't need n eigenspaces, right? Because each eigenspace could have a dimension more than one, based on its geometric multiplicity, okay? And 4, the sum of the geometric multiplicities of distinct eigenvalues is the dimension of V. So these are things that we've kind of already looked at in detail before, and this is kind of telling us that it's diagonalizable if and only if we have a basis of eigenvectors, okay? And these two are kind of just saying that we have a basis of eigenvectors. All right, so let's look at an example now from 2501. Let V be a vector space and V1, V2, V3 is a basis for V. Let T be a linear map from V to V such that T of V1 equals 2V1 plus V2 plus V3, T of V2 equals 2V2, and T of V3 equals V2 plus V3. Is there a basis for B such that the matrix of T with respect to B is diagonal? Explain. So first of all, let's find the matrix of T with respect to the basis B, with respect to basis B, which is V1, V2, and V3. So keep in mind that, you know, with respect to my basis, right, V1 has coordinate vector 1, 0, 0, V2 has coordinate vector 0, 1, 0, and so forth, right? So this is kind of telling me that T of V1 equals, in respect to my basis B, that is, equals 2, 1, 1, okay? And T of V2 with respect to my basis B equals 0, 2, 0. And T of V3 with respect to my basis B is 0, 1, 1. Okay, so the representation of the matrix with respect to the basis B will be this. So the matrix, so T with respect to B in the domain and codomain is 2, 1, 1, 0, 2, 0, 0, 1, 1. Okay? And again, that's the same process we looked at last time. You kind of just see, all right, where do my basis vectors go under the linear transformation? Now the question is this diagonalizable? Okay, and now in order to check whether it's diagonalizable, we kind of need to look at these conditions. So the main question is there a basis of V consisting of the eigenvectors of T? Okay, and in order to do that, one way is to look at our last condition, and that is to find all the geometric multiplicities for distinct eigenvalues and sum them together. And the question is, do we get 3? Okay, so the characteristic polynomial, if we actually find it, should be this. Okay, so we have lambda 1 equals 2, lambda 2 equals 1. Okay, and so we have, this has algebraic multiplicity of 2. And so we'll need to check the eigenspace E2 equals the kernel of A minus 2i. So checking the kernel of A minus 2i, okay, because we don't really have to investigate this one because it has algebraic multiplicity of 1, so that's okay. We need to look at the kernel of A minus 2i. And if we actually bother to find it, what we'll see is that that's equal to this kernel here. Okay, Now, if we look at this, right, this dimension, the dimension of this kernel is 1, okay? And therefore, if that's the case, then you can see that the geometric multiplicity of 2 equals 1, which is less than 2, okay? And what that means is if we sum the geometric multiplicities for distinct eigenvalues, we get uh, 2, which is less than 3, which is the dimension of V. So there will not be an eigenbasis, and therefore there will be no representation for which the linear map is diagonal, okay? And therefore T cannot be diagonalized. Alright, so now we're going to move on to a very important theorem for eigenvectors, eigenvalues. This is the spectral theorem. So again, this is primarily covered in Math2601, but it's worth knowing for Math2501 for specific cases. So first of all, we'll look at a definition here. A linear transformation is normal if and only if it commutes with its adjoint. That is, t of t star equals t star of t. Okay, and that sort of extends to matrices. If we have a star equals a star a, that means we have a normal matrix because it commutes with its adjoint. All right, so if we are looking at normal matrices, then we can see we have some properties here. The length of TV equals the length of T star V. If T is normal, then T minus alpha times the identity map is normal, okay? And this is sort of playing into the fact that this is very similar to what we're working with when we're working with eigenspaces. Now, the eigenspace T with eigenvalue lambda, so it's E lambda of T, is equal to the eigenspace of lambda bar, so that's the conjugate, of the adjoint T star, okay? So if I look at some eigenspace, okay, of T with eigenvalue lambda, then the eigenspace of T star with the corresponding same basis, same everything, the same vector space, will have eigenvalue lambda bar, so that's the conjugate, complex conjugate. If T is normal, then the two eigenspaces corresponding to distinct eigenvalues are orthogonal. Okay, so this is important here. If I have distinct eigenspaces, then they are orthogonal. So we'll have these two are orthogonal. We saw earlier that the intersection of these would be the zero vector, but now we can see if we're working with normal maps, then they're actually orthogonal. And so we have a set of orthogonal eigenvectors, eigenspaces, sorry, yeah. So now what we're going to look at is the spectral theorem, so the important theorem here. So if we're working with a normal matrix, then the eigenvectors corresponding to distinct eigenvalues are orthogonal. This is a sort of extension of this idea, okay? Then there exists a unitary matrix Q such that Q star AQ equals Q transpose AQ is diagonal. Okay, so what this is telling us is that essentially what we have is that if we have a normal matrix, okay, we have orthogonal eigenvectors. Okay, if we have orthogonal eigenvectors, it's kind of telling us that, okay, we have a full set, we also have a full set of orthogonal eigenvectors. So the normal matrix will be diagonalizable, okay? And remember, if it's diagonalizable, then we can say, okay, Q inverse AQ will be equal to diagonal matrix, right? Now, keep in mind that, what is this matrix Q? Remember, Q is sort of that matrix that helps us convert between, I guess, any basis and our eigenbasis, right? And now, if I have Q, okay, that Q equals a matrix with all my eigenvectors, okay? Okay, if I have a set of orthogonal eigenvectors, then I have a matrix with orthogonal columns, giving me a unitary matrix if it's all normalized, right? So that's telling us that, and remember that unitary matrices are matrices where the adjoint is equal to the inverse, right? So it's telling me that any normal matrix is unitarily diagonalizable, which means we can diagonalize it in terms of a unitary matrix like this, okay? And now my third conditional is, oh, well, I guess the third condition depends on now the specific type of normal matrices. So I forgot to mention earlier that with normal matrices, I guess some special adjoints that we looked at earlier was self-adjoint, and unitary matrices, right? So both self-adjoint and unitary matrices are normal, okay? So we can extend the spectral theorem to self-adjoint matrices, for example. Remember, self-adjoint means it's either Hermitian, okay, if, well, in the complex case, okay, or symmetric in the real case. Okay, now because Hermitian symmetric matrices are normal, then the normal or the spectral theorem applies to them, okay, which means that there exists an orthogonal or unitary in the complex case matrix Q such that Q inverse AQ is diagonal. So this is saying that self-adjoint matrices are unitarily diagonalizable, which is exactly what we looked at previous, right? But we also have this additional condition that all the eigenvalues are real. So all the eigenvalues for self-adjoint matrices are real. Now we can also look at unitary matrices, right? Which again, remember in the real case, unitary matrices are orthogonal matrices. Okay, so for orthogonal matrices, again, they're normal matrices, which means by the spectral theorem, they're unitarily diagonalizable. But also we have this other condition here that all the eigenvalues lie on the unit circle in the complex plane. Okay, that's equivalent to saying they all are of the form e to the I alpha k. Alright, so let's look at an example of the spectral theorem to see what's going on. So let P be the matrix 1 on 9 and all these entries here. We may assume that P is orthogonal. Okay, so first of all, show that kernel of P minus I equals the span of these two vectors. So to do that, first thing to look at is the kernel of P minus I is equal to the kernel of this matrix here. Okay, what we've done is sort of ignored that 1 on 9 out the front, which won't affect the actual kernel, and then subtracted 1 along all the diagonal entries. Now, if we row reduce, what we'll get is this here. So if we row reduce, we'll get this here. Now, the question is that show that the kernel is equal to the span of these two vectors. Okay, all we have to do is show that, all we have to do really is show that, sorry, 1, 0, 0, 1 transpose is an element of kernel P minus I. Same with 1, 4, 0, negative 1 transpose is an element of kernel P minus I. Further, you can see that these two vectors will have to be linearly independent, right? Because the entries here, we have a 0 there and a 4 there, right? So you can see that if we have two linearly independent vectors, that would imply that the kernel of P minus I has dimension 2. And we can confirm that by looking at our matrix here, we can see that the nullity of this is 2, okay? And so because each of these two vectors is an element of the kernel, and we could check that by multiplication, but we'll see that we get them. We'll get that they're elements of the kernel. And so because they're linearly independent, they form a basis for kernel P minus I. Alright, so if that's the case, let's actually see what we've done. This is saying that these two are eigenvectors with eigenvalue 1. Okay? So now the second part of the question is explain why the spectrum of P, so that's a set of all eigenvalues, is 1, 1, I, negative I. So you can see that we have two linearly independent eigenvectors with eigenvalue 1. So you can see that the geometric multiplicity of eigenvalue 1 is 2. Now, if the geometric multiplicity is 2, then that's saying the algebraic multiplicity, well, we know that the geometric multiplicity is always less than or equal to algebraic multiplicity. Okay, so we could say, all right, then we can see that at least 1, 1 have to be eigenvalues. There has to be at least two eigenvalues with value 1, right? So we can kind of see, all right, therefore, um, therefore we have 2 eigenvalues, 1. Now, keep in mind that what we have is an orthogonal matrix, okay? So this is where the spectral theorem comes in. By the spectral theorem, this is diagonalizable. It's unitarily diagonalizable by the spectral theorem, okay? Because it's orthogonal, remember orthogonal matrices are normal, so it applies to them. So if it's diagonalizable, remember that's equivalent to saying that geometric multiplicity for each eigenvalue equals the algebraic multiplicity for each eigenvalue. Okay? So that's telling us that 1 must have algebraic multiplicity of 2. Alright? In which case it appears twice. Now we found 2 out of 4 of the eigenvectors. We have to find what are the other 2. So now here's where the trace comes in. You can see that the trace of this matrix will be 5 on 9 plus 8 on 9 plus 5 on 9. We get 2. So we can see that the trace of the matrix, trace equals 2. So we're saying 1 plus 1 plus lambda 3 plus lambda 4 equals 2. So lambda 3 plus lambda 4 must equal 0. Now we have this result again for orthogonal matrices by the spectral theorem. So by the spectral theorem, okay, for orthogonal matrices, which is sort of the real version of unitary matrices, we can see that all the eigenvalues lie on the unit circle. So what we need is for these to lie on the unit circle as well. So what we have is two eigenvectors that sum to 0 and lie on the unit circle. So if you look at the unit circle here, you can see that, okay, the question is, okay, what are 2 values that add to 0? So you can see that 1 and negative 1 lie in the unit circle that add to 0. But we can't do that because if we had 1 and negative 1, then that would say that 1 has AM3, which is what we've already shown not to be the case because it's diagonalizable and the geometric multiplicity is 2. Algebraic multiplicity can't be 1, right? Now we also know that these 2 values must be complex conjugates. Must be complex conjugates. And the reason why that is because if you look at our characteristic polynomial is a real polynomial, right? Which means it has real coefficients, okay? Which means that if it had complex roots, they must come in conjugate pairs, okay? And so the question is, what complex conjugates add to 0 and lie in the unit circle and aren't 1 and negative 1? And the only options in that case are I and negative I. So you can see that any other complex conjugates would sort of lie here and here and wouldn't add to 0. Okay, so this leaves only I and negative I as the other eigenvalues. Hence, our spectrum is 1, 1, I, negative I. Okay? Alright, so now let's move on to some sort of applications of eigenvectors and eigenvalues. So first we're going to look at a rotation matrix. So a rotation matrix is of the form cos alpha minus sine alpha cos alpha. And this sort of rotates us by alpha radians. So e to the I alpha is an eigenvalue of this linear map. Okay, that's sort of telling us that um, this sort of corresponds again to rotation by alpha. Okay, so now let's look at this theorem here. So if I have an orthogonal matrix in a 3D vector space, real vector space. So consider Q to be 3 by 3 orthogonal matrix, so that its columns are an orthonormal basis for the vector space. Then Q is unitarily similar to one of the following 2 matrices. So it's either unitarily similar to this or unitarily similar to that. Keep in mind, what does unitarily similar mean? unitarily similar means that it's similar. So we can say Q equals say P inverse AP, right? Where P in this case would have to be a unitary matrix. Okay? So unitarily similar means that the matrix sort of changing our bases here is a unitary matrix. All right. So if you look at this matrix, we see that this is actually a rotation about the x-axis by angle alpha, okay? And this one is a reflection about the YZ plane composed with a rotation about the x-axis, okay? This has determinant 1 equal to 1, okay? And this has determinant equal to -1. All right, so we have another theorem here. For an orthogonal matrix Q, if the determinant Q equals 1, then Q is unitarily similar to 1. Okay, so that's you can kind of see that one of our similarity invariants, remember, was determinant. Okay, so if the determinant is 1, it needs to be similar to this. Now, if the determinant is -1, then it needs to be similar to this. And what that's telling you is that if determinant 1 is this, then it's similar to a matrix that represents rotation about the x-axis. And if it has determinant -1, then it corresponds, or it's similar to a matrix that corresponds to reflection and then rotation. So you can kind of see if we take an orthogonal matrix Q, if its determinant is 1, then it corresponds to rotation. If its determinant is -1, then it corresponds to reflection and rotation. Okay. Now, if we actually want to find the angle of rotation, okay, we can see that trace is a similarity invariant. Okay, we saw that last seminar or in the previous topics, right? So if it's a similarity invariant, then for all similar matrices, the trace is the same. So if I have a matrix that's similar to this matrix, so if I have an orthogonal matrix that's similar to this, okay, in other words, its determinant is 1, then the trace is the same. So we can see that 1 plus 2 cos alpha, which is the trace, must equal to the trace of our matrix Q, okay, because that's the similarity invariant. And therefore, because alpha is the angle of rotation, 1 plus 2 cos alpha equals trace Q gives us the angle of rotation. And that's very similar for the second one. In this case, it will be -1 plus 2 cos alpha. So we can find angle of rotation by looking at trace. All right, so now let's look at a particular example. So give a geometric description of 1 on 9, 4, 4, 7, 8, 1, 4, 1, 8, -4. So in order to find a geometric description, we ask some questions. So first question should be, is it orthogonal? Okay. If it's orthogonal, is det A equal to 1 or det A equal to -1? Because remember, if it's orthogonal, then it is unitarily similar to one of these two rotation matrices, or rotation reflection matrices. And now it will be a rotation if det is 1, and it'll be a reflection and rotation if det equals -1. All right, so now looking at this, we're going to check, is A orthogonal? Now, to check whether it's orthogonal, it's a matter of proving that all our columns are mutually orthogonal, okay? And if we actually did that, we'll see that, okay, they are mutually orthogonal, okay? And then now let's look at the determinant. So to check the determinant, it's just, we'll have to calculate it for a 3 by 3 matrix, and if we do, we'll get 1. Okay? So we'll get 1. And if you see this 1 on 729 is because, remember, we're sort of multiplying each of these rows by 1 on 9, and so the determinant will have a factor of 1 on 9 cubed out to the front. Okay, so because determinant is 1, then it must be a reflection. So a rotation. My bad. Rotation. And so the question is, for us to give an actual geometric description, what we really should find is the angle of rotation, like how much it rotates by, and the axes of rotation. So about what axis is it rotating? Okay. Now to find the axes of rotation, let's look at this theorem. So for an orthogonal matrix similar to 1, the eigenvector corresponding to eigenvalue 1 is the axis about which the rotation matrix occurs. So the reason why this is because we're finding some vector that is invariant under the rotation. So it points in the exact same direction, and further, its length hasn't been scaled. So if that's the case, then this must be the axis of rotation. So if we're rotating about this axis, right, for example, like this, right, you can see that that vector will remain invariant under the rotation, which is exactly how eigenvectors are defined, right? And so we look at this other theorem for an orthogonal matrix similar to 2. The eigenvector corresponding to eigenvalue -1 is the axis about which the rotation matrix acts, perpendicular to the plane across which it is reflected. So sort of -1 corresponds to our reflection. All right, so let's look at this particular case. So we want to find the eigenvector corresponding to 1. To do that, remember we'll have to solve to find the kernel of a minus I. But if we did do that, we'd see that a vector, an eigenvector, is 2, 3, 2 transpose. Okay, so the axis of rotation will be around the axis 2, 3, 2 transpose. All right, to find the angle of rotation, remember that our trace will be 1 plus 2 cos alpha. And so if we find the trace, that's -2/3. So cos alpha equals -5/6. So alpha equals cos inverse -5/16. And that will be our angle of rotation. Okay, so to summarize, A will be a rotation about the axis 2, 3, 2 by an angle of cos inverse 5/6. All right, perfect. So let's move on. So moving on to conics and quadrics. So another application of eigenvectors and eigenvalues is to find or sort of identify general conics and quadrics. Like given a certain equation, what is the actual surface that it represents? Now, for terms that only involve x squared, y squared, and z squared, it's fairly okay to determine what it is. So if we look at the two-dimensional case, if I look at something like this, I know this is a ellipsoid. Okay, and to determine that, it's just by looking at the signs. If we add them together, we'll get an ellipsoid. Now, if one is negative, then what I get is a hyperboloid. Okay, and um, it's sort of like that. And if I had 1 is 0, then I get a plane and so forth, right? However, we come into some issues when we have x, y sort of terms, like terms like this. And in terms of these terms, what do they actually represent? They represent a sort of rotation of a quadric. So we like it's sort of if we take a representation of a quadric only using x squared plus x squared, y squared, and z squared, if we add terms like x, y, y, z, etc., they correspond to sort of rotating this surface. Okay, so to identify to actually identify what rotation this is, we can use eigenvectors, right? So in particular, let's look at an example and it'll sort of help us see what's going on. So let's given this surface, find the principal axes, the type of surface, and the points, if any, on the curve which are closest to the origin. So to do this, we'll always represent it in the form x transpose a x equals c, where x is x, y, z, and a is symmetric. So we need a to be symmetric. All right. And now the reason why we do that is because for symmetric matrices, they have nice properties that we've already seen by the by the spectral theorem. Okay, so in particular, that's saying that we can diagonalize them orthogonally. All right, so what we sort of need to do is first find it in the form x transpose a, and then we'll find the eigenvectors and eigenvalues. Okay, and then we'll diagonalize it. Okay, we'll diagonalize it in terms of an orthogonal matrix. And so what we can kind of do is then identify our new axes of the form our old axes rotated by Q, which is an orthogonal matrix. Okay, so if this is a bit confusing, we'll go into the example, right? So first of all, we can identify this curve as this. So we need to find the actual symmetric matrix that represents it. And in this case, it is 5, 3, 4, okay, along the main diagonal. So you can kind of see that because we have 5, 3, 4 here. So it's kind of like x, y, z, 5, 3, 4, 5, 3, 4, x, y, z. And you can see that that will give us these terms, okay? And then to get these terms here, we'll see that it needs to be 0, 2, 2. And the reason why that is because this will correspond, this here corresponds to our xy, and these two will correspond to our xz and yz and so forth. And we can see that if we multiply by the left and right, we'll add them together. So that's why it's 2 and not 4. So 2 plus 2 is 4. And this is our symmetric matrix. Okay. All right. Now let's calculate the eigenvectors and eigenvalues. So we've done that before already. So we'll take for granted that these are our eigenvectors and eigenvalues. Okay. Now what we need to do is diagonalize. Okay. So to diagonalize it, right? We're going to sort of say we'll have A equals QD Q transpose, but for Q orthogonal. Okay? And if that's the case, what we need is our 3 columns. So Q will be columns with our eigenvectors. Okay? We just need to keep in mind that in order for it to be orthogonal, we'll just need to scale the vectors have magnitude 1, so they form an orthonormal basis. Okay, now keep in mind, by the spectral theorem, because we have a symmetric matrix, right, these are already orthogonal, okay, by the spectral theorem, so they're already orthogonal. That's fine, we don't have to check that. We just have to scale their magnitude, so scale magnitude. So for example, for the first one, it will become 1, negative 2, 2 becomes 1 on the square root of 1 plus 4 plus 4, which equals 3, negative 1, negative 2, 2. And we'll keep doing that, and then this is our matrix Q, okay? And that's very nice, because then we can say Q transpose, then we can say that A equals Q, D, Q transpose, for D is diagonal, and in particular, D will correspond to our eigenvectors, okay? And so, sorry, eigenvalues. So D will be diagonal, and we just look at each vector and its corresponding eigenvalue. So it'll be 1, 4, 7, 1, 4, 7, and that's our diagonal matrix. Okay, and so we'll diagonalize A like this. So once A is diagonalized, how does that actually help us find what the surface is and its principal axes? Well, let's keep in mind that what we have is x transpose AX equals 1. So that's saying that x transpose QD Q transpose X equals 1. And that's Q transpose X T transpose D Q transpose X equals 1. So it's a bit of a mouthful, but what we get is this. And the reason why that's useful is because you can see what we have is some X transpose DX, where X equals Q transpose X. Okay, now the reason why this is so useful is because if I have a diagonal matrix, right, I can say x equals x, y, z, right? And if it's diagonal, then I have, well, remember from previous, that's 1, 4, 7, and then we'll have x transpose x here equals 1. That will give me x squared plus 4y squared plus 7z squared equals 1. Okay? Because it's very nice with these diagonal matrices. If we just want to expand it all out, it'll be very nice. It'll just be like this, right? And you can see that what we have is a corresponding quadrate, like surface here, without the problematic xz, yz, etc. terms. Okay? And so we can easily classify this. This can be classified. This will just be a ellipsoid because we have positive signs, okay? And therefore, we can conclude that the original surface is an ellipsoid. And the reason why that is because like if we actually look, what is the vector x? Okay, it's new coordinates x, y, z, but we said it was q transpose times the original coordinates. Okay, and remember that because q transpose, in this case q, will be orthogonal, and so is q transpose, we can conclude that it's unitarily similar to some rotation, right? And so or reflection, right? So we can conclude that we're sort of the only thing we're doing is taking our original surface, and if we rewrite it like this, we're just rotating it. Okay? So we're not actually changing the actual surface, right? So that's perfect. And so we can conclude that this is an ellipsoid because sort of once we rotate it, it gives only positive signs, and therefore it's an ellipsoid. All right. So in more detail, essentially the idea here is that once we find the shape in the capital X domain, we know that the mapping here is actually a bijection, okay? Because of the properties of the orthogonal matrix Q. And so any point on our surface in the X, Y, Z domain is sort of the corresponding point in X, Y, Z lowercase, but just rotated by multiplying by Q. Okay? So we can see that the 1, 0, 0 original axis gets mapped to this axis. The 0, 1, 0 axis here becomes this axis, and the 0, 0, 1 becomes this axis. So here, okay? In other words, just by multiplying by q. So the reason why that is because to go from our capital X coordinates to our lowercase x coordinates, we multiply by q. And so therefore we can say, in order to find the principal axes, which is one of our goals, okay, all we need to sort of look at is the eigenvalue, the eigenvectors, okay, because they sort of um, remain constant under the transformation. So our eigenvectors will be our principal axes, and in order to find this last one, which is points that are closest to the origin, all we need to kind of do is look at our x curve. Okay, so in our x curve, we have x squared plus 4y squared plus 7z squared equals 0. And we want to find, okay, what's the point closest to the origin? In this case, the point closest to the origin for this curve should just be when xy is 0, and then what we get, oh, sorry, it should just be 0, 0, 1 on root 7. Okay, and now, so that's not 0, that's equal to 1, yeah. And so when x, y is 0, we see that z equals 1 over root 7. Okay, and now to find the point closest with respect to our original coordinates, okay, remember that a coordinate in x, to get a coordinate in lowercase x, all we need to do is multiply by q. Okay, so we'll take this and we'll multiply by q, and we'll get 2, 3 root 7, 1 on 3 root 7, 2 on 3 root 7, and this will be our result. Okay, so now you can see that in terms of classifying the shape, or what surface it actually is, you can kind of see that what we had is x transpose times our diagonal matrix, which is corresponding to our eigenvalues like that, and this will give us the corresponding curve lambda 1 x squared plus lambda 2 y squared, so forth, right? So the only thing that's important is actually the signs of the eigenvalues, right? Because remember, we're looking at the signs of these x squared, y squared terms, and if we rewrite it like this, that's just dependent on these diagonal entries, right? So if we have 3 positive eigenvalues, it's an ellipsoid, 2 positive, 1 negative, and it's a hyperboloid of 1 sheet, so forth, right? And we can kind of use this to identify quickly just by looking at eigenvalues. Okay, so we're done with this sort of application, and now we'll move on to singular values, which is in Math2601. So in terms of singular values, I guess before we look at the definition, it's useful because we're sort of taking a matrix A and we're factorizing it in this form. U sigma V star, okay? Where U is an m by m unitary matrix, V is n by n unitary matrix, and sigma is m by n matrix with these entries, okay? Keep in mind this is for A is an m by n matrix. So given any m by n matrix, okay, we can find a factorized form. So remember that QR factorization from previous, we could only factorize QR if it had full rank. If full rank. In this case, we don't need extra condition of full rank, so we can just factorize it, okay? And that's not, it doesn't even have to be square, it's just m by n, okay? So in terms of this decomposition, sigma will be the matrix that's called our singular value matrix, okay? So singular values will be the square roots of the eigenvalues of A star A. And it's a bit confusing if you haven't seen this before, but the sort of process will make this a bit more clear for why we define these things these ways. But the actual matrix sigma will have only singular values on the diagonal entry, okay, and will elsewhere be filled with zeros. Okay. All right, so let's actually just look at the algorithm now, which will make this a bit more clear. So the first method of doing it is to find all n eigenvalues of A star A and write them in descending order. Also find the corresponding eigenvectors once we put them in unit length, okay? Then compute ui equals 1 on square root sigma I a vi for each non-zero eigenvalue. Then extend this to an orthonormal basis of complex m-dimensional vector space using Gram-Schmidt process. Then form U and V. So U will have columns UI and V will have columns VI, and form sigma from the singular values. So what we do is we look at all the square roots of the eigenvalues, okay, and then fill in the matrix to be zeros elsewhere, so it's an m by n matrix. All right, so one way of speeding up this algorithm is that A star A and A star share the same non-zero eigenvalues. Second, if rank A equals Q, then A star A has Q non-zero eigenvalues. All other eigenvalues are zero, okay? So this is useful for when n is greater than m, since A star A is an n by n matrix, whereas A star is an m by m matrix. So I'll explain that like this. The goal is to find the eigenvalues of A star A. Okay, you can see that that's the important thing for the algorithm, okay, because this will give us our singular values, the square roots of the eigenvalues, okay? Now the question is, this is sort of a long process. You've kind of see that finding eigenvalues can be a bit tedious, right? So the question is, how do we speed this up? So we know that we have m by n a, which implies that A star A is n times n versus A star is m times m. And we can kind of see also that if n is larger than m, okay, this will be a longer process. And by the theorems that we've kind of seen here, we see that they share the same non-zero eigenvalues anyway. So if m is smaller, it's quicker to just do it by this way, because we will have to find, we'll spend less time because it's a smaller matrix, right? So let's actually just look at the example, and it'll make it a bit clearer what's going on. So we'll follow the algorithm. In this case, we're given some parts that will help us out a bit. So given the matrix A equals 3, -1, 1, 3, 1, 1, you can kind of see already that this is a 2 by 3 matrix. Okay, so it is faster to find A star eigenvalues anyway. And that's the first part. So the first part is to find the eigenvalues of A star. So we'll first compute A star. So A star equals this matrix here. Okay, and so you can see that the eigenvalues must add to 11 plus 11 equals 22, and they must multiply to give us 120, which is 11 times 11 minus 1. All right, And I guess in this case, by inspection, you kind of see that lambda 1 equals 10, lambda 2 equals 12. Oh, sorry, lambda 1 equals 12, lambda 2 equals 10. And the reason why we like to do that is because the singular values are ordered in descending order. That's sort of how we define them, okay? So they've got to be ordered in descending order. Okay, so once we've done that, we've found the eigenvalues. That's part 1 done. Now part 2, explain why the eigenvalues in part 1 are also eigenvalues of A star A, and state any other eigenvalues of A star A. So A star A and A star share the same non-zero eigenvalues. So 12 and 10 must be eigenvalues of A star, and the rest, or the other eigenvalues of A star A must be 0. So remember that A star A will have maximum 3 eigenvalues. So we'll have 12, 10, and 0 are the eigenvalues. Okay. So now part 3 of this question is find the eigenvectors of A star A. So to find the eigenvectors, we'll have to compute A star A. We'll get this here. And in order to do this, we already know that 12 and 10 and 0 are the eigenvectors. So really all we have to do is find the kernel of A star A minus 12i, the kernel of A star A minus 10i, and the kernel of A star A. Okay, if we actually do that, we'll see that our eigenvectors are 1, 2, 1, negative 2, 1, 0, and negative 1, negative 2, 5. Okay, and so next thing we need to do is normalize the eigenvectors, okay? And we'll get this. Now part 4 is to find the singular value decomposition. Alright, so remember for our singular value decomposition, our vector V, sorry, our matrix V, sorry, will have columns V1, V2, V3, okay? And that will be, in this case, given by these vectors here. So we've already found V, that's all good. Now we just need to find U. So to find U, remember that each UI, each column, will be 1 on square root lambda I, AVI, for each non-zero eigenvector. So if we actually do that, we'll see that U1 equals 1 on root 2, 1, 1, U2 equals 1 on root 2, negative 1, 1. So you can see that U will be a 2 by 2 matrix, right? So we need to complete this to a basis for this vector space. However, we can see that we've already got 2 linearly independent vectors, so we don't have to actually do the Gram-Schmidt process. Now, keep in mind, if this was the other way around, okay, if our matrix was this matrix instead, just the transpose, then it would be a bit more annoying because we'd have to complete it to a basis for C2, but in this case we don't. Alright, so now we've got we've got the columns of V and we've got the columns of U. And now in order to complete it, we just need to say what is sigma. So sigma is, remember, in this case needs to be a 2 by 3 matrix where the diagonal entries are the non-zero singular values, in this case, the square roots of them, sorry. And if that's the case, then these will be our diagonal entries, and then we complete it to a 2 by 3 matrix by just adding zeros elsewhere, and we'll get this, okay? And so U will just equal the columns here. These are our 2 columns. V will equal the matrix with these 3 columns, and sigma is just this matrix here. And so this is our SVD, U sigma V star. All right, so I've finished eigenvectors now, and so we'll be moving on to Fred's part where he'll take on Jordan forms.
Alrighty, looks like we're in. So I'm Fred. I'm going to be taking the last two topics, the Jordan canonical form and the matrix ODEs. Alrighty, now the very first thing we get into is looking at Jordan blocks, and we begin by the definition of a k by k Jordan block. Alright, now the definition is, if we have a k by k Jordan block for the lambda, we write it as the j, where we have subscript k, and inside the brackets is our lambda, and along the diagonal we have our lambdas, and along the super diagonals, so that's the entries directly above the diagonals, we have our ones. Okay, and this is going to be a k by k matrix. Okay, so Jordan block, we just chuck in our lambdas on the diagonals, and immediately above our diagonals node, called the super diagonals, we put in ones. Okay. Oops. Quick examples here. Now, J3 of -4, so this indicates we have a 3 by 3 matrix, and this indicates that we have -4 on the diagonals, followed by ones along the super diagonals. Okay. J4 of 0, so this is going to be a 4 by 4 matrix with zeros along the diagonals and ones along the super diagonals. Alright, and that's some quick examples for Jordan blocks. Now, the good thing about Jordan blocks is that they are relatively easy to calculate the powers of. Notice that if we have J1 of lambda, so that's just the 1 by 1 matrix, so J1 of lambda is just lambda. If we take J1 lambda to the power n, this is pretty intuitive, we just get lambda to the n as our single entry. Okay. If we notice J2 of lambda, okay, so this would be lambda, lambda, 1, 0. If we take it to the power n, we would get lambda to the n in the diagonals with this n choose 1 lambda to the n minus 1 in the entry directly above the diagonal. Okay. If we continue on this pattern, you'll notice if we look at J3 lambda to the power n, we have lambda to the n in the diagonal, n choose 1 lambda to the n minus 1 in the entry directly above the diagonal, and n choose 2 lambda to the n minus 2 above that. Okay, and we can keep generalizing this notion if we look at J4 lambda to the n. Again, lambda to the n in the diagonals, n choose 1 lambda to the n minus 1 in the super diagonals, n choose 2 lambda to the n minus 2 in the directly above that, and then lastly n choose 3 lambda to the n minus 3 above that. Okay, and notice these expressions here, they are just from the binomial expansion of lambda to the 1 to the power n, and that gets you like lambda to the n plus n choose 1 lambda to the n minus 1, and so on. Okay, and the quick proof for this is that, let's consider the 3 by 3 case where we have lambda, J3 of lambda is equal to, actually let's use blue. Okay, let's use blue. Now let's consider the case where we have J3 of lambda, that's going to equal to lambda, 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 1, 1, and 0 above there. Okay, we can rewrite this as lambda times the identity matrix 1, 1, 1, plus the, so we have zeros in the diagonal, plus the 1, 1s in the super diagonals. Okay, and if we power this to the n, right, we power this whole expression to the n, and then we just apply binomial expansion to this sum here, lambda times the identity matrix plus this ones in the super diagonal matrix. Okay, and if we expand it out, that we just get our expressions like we have over here. Okay, Alright. Now, this is what I said previously. So we start by putting lambda to the n in the diagonals. So lambda to the n on the diagonals, put n choose 1 lambda to the n minus 1 immediately above. Keep repeating this pattern where we increase the binomial coefficient and decrease the power until you pad out the entire size, whatever the size of your Jordan block should be. Okay? And if you ever bump into the n choose n, that's our last binomial coefficient, and that actually turns out to be the last diagonal that you actually fill. If you have more space above your Jordan block, just pad it with zeros everywhere above. Okay. Now, definition here, we have a direct sum of matrices. Now again, we represent direct sums using these plus with a circle around. Now, direct sum of, let's say, n matrices A1, A2 to AN, how we define that is we put A1 in the top diagonal, we put A2 in the diagonal to the bottom right, and we keep repeating this pattern until we have this matrix here, and we pad everything else out with 0. Okay, so a quick example, if we have, let's say, J1 of 2, and we direct sum this with J2 of 1. Okay, so what this looks like is J1 of 2 is just going to be the single entry here, and we direct sum this with the Jordan blocks of 1s. What this is going to look like is we chuck the 2 out here, and we chuck the second matrix directly to the bottom right of it, and we pad everything else out with zeros. Okay, so that's what it's going to look at when we have a direct sum of Jordan blocks. Okay. Again, quick example here. Notice that if we take the direct sum of J23 with J45, we just chuck this in the top left, and we chuck the second matrix directly to the bottom right of it, and pad everything else out with zeros. Okay. Quick lemma here: if we take the power of the direct sum of Jordan blocks, that is the same as taking the direct sum of the powers of Jordan blocks. Okay, so in this case here, this n here, we just chuck it straight inside, and that they are going to be equal. Okay. Again, example here, we have J23 direct sum with J12 to the power n. So what this is going to look like is J2 of 3 is just going to be this Jordan block here, and we direct sum it with J1 of 2. That's just going to be the single entry to the power n. Okay, and again, we can just chuck the n inside of the direct sum of matrices and take the power individually to get us a direct sum of these two matrices together, and we pad everything else out with zeros again. Okay. And we get on to our next definition, known as the generalized eigenvector. Now, a generalized eigenvector corresponding to an eigenvalue lambda is a non-zero vector again. Remember that your eigenvector can't be non-zero, and same thing with a generalized eigenvector, can't be 0. And it has to satisfy this property here, a minus lambda to the power k, v equals 0 for some integer k. Okay, and this actually generalizes the notion of an eigenvector, because we know that an eigenvector, a minus lambda I times v must equal to 0. Okay, so an eigenvector is just the special case where we take k equals 1, whereas a generalized eigenvector, we actually generalize it to, we can take any power of k. Okay. Quick example here. So suppose we have matrix C and we have a vector V. Show that for the matrix C, V is a generalized eigenvector corresponding to lambda is equal to 5. Okay. So all we have to show is that we can find some value of k such that a minus lambda I to the k times v is equal to 0. Okay. We start with looking at c minus 5i, and we multiply that with v. Okay. If we multiply c minus 5i with v, we get 1 minus 1, 1, 1. So that's clearly not the 0 vector, so we have to apply, we have to multiply by c minus 5i squared, check if that is going to get you the 0 vector. Okay. And if we notice this guy here, c minus 5i all squared, we don't actually calculate the matrix all squared because that's going to take like a really big effort. What we instead do is we actually calculate c minus 5i times c minus 5i times the vector v, which was what was the vector v? 1 minus 2, 3. Okay, so we actually multiply this by 1, oops, minus 2, and 3. And we know that this part here, right? This part here corresponded to minus 1, 1, 1. Okay, and here we're just doing, again, a matrix times a vector, which is a lot simpler than squaring a matrix and then multiplying by a vector. And this turns out to be the 0 vector. Okay. And since c minus 5i squared times v is equal to 0, that's going to tell us that v is a generalized eigenvector corresponding to lambda is 5. Okay. And moving on to generalized eigenspace, this is very similar to the notion of eigenspaces that you guys have learned in chapter 6. A generalized eigenspace denoted as GE lambda of A, so it's this guy here, is a set of all generalized eigenvectors A corresponding to lambda. Okay, so remember that the eigenspace of lambda is the set of all eigenvectors corresponding to lambda. Same thing with generalized, we just add a generalized in front. Okay, so in terms of math language, we have the set of all vectors v such that a minus lambda I to the kv is equal to 0 for some integer k. Okay, this is just a set of all generalized eigenvectors. And we can actually represent this using a notion here. If we take the intersection of the case where k is 1 with k is 2, k is 3, and so on, that would get us the generalized eigenvector for lambda. Okay. And the definition here we have is a Jordan matrix. So a Jordan matrix J is just simply a direct sum of Jordan blocks. And the reason why we define Jordan matrix is because later down the line we can actually see that every single matrix can be reduced down to a Jordan matrix. Back chapter 6, you know that not every matrix is diagonalizable, but in chapter 7, we can actually prove that every matrix is actually, we can actually reduce it down to a Jordan matrix. Okay. Again, we want to mimic diagonalizable matrices as much as we can, but again, not every matrix is diagonalizable, so that's where the Jordan matrix comes in. And number 2 is that the Jordan form of matrix will become its complete similarity invariant. And what this means is that two matrices, they're going to be similar if and only if they have the same Jordan form. Okay. Now, you notice that let's say determinant, eigenvectors, eigenvalues, trace, rank, nullity, they were all similarity invariants, but they weren't the set of complete similarity invariants. Okay, just because two matrices have the same determinant doesn't mean they're similar. But in this case here, if two matrices have the same Jordan form, then that's going to tell you that they're going to be similar. Okay. And quick lemma, every matrix A has one and only one Jordan matrix up to some permutation of Jordan blocks. What this means is that if we have a Jordan matrix, let's say j1 of 2, direct sum it with j2 of 3. Okay. Let's say our A is similar to this matrix here. Okay. We can also say A is similar to this second Jordan matrix, j2 of 3, direct sum it with j1 of 2. Right. Notice that all I've done was just swapped the orders around to write j2 of 3 in front of j1 of 2. And these two, that's what we call like up to some permutation, because we can always swap the orders of our Jordan blocks around. But in the end, we still have the same set of Jordan blocks. We just like arranged it differently. Okay. Okay. A couple of useful properties. Now, if we denote the nullity of a minus lambda I to the power k as just dk, then we know that d0, that represents the nullity of a minus lambda I to the power 0, which is just the nullity of the identity matrix, which is just going to be 0. Okay. Then we know that the kernel of the power 0 is going to be a subset of kernel to the power 1, which is subset to the kernel of the power 2, and so on. Okay. The reason why this is true is because if we know that a minus lambda I times some vector v is equal to 0, then we can just simply multiply the left of this equation by a minus lambda I. So a minus lambda I times 0, and we get that a minus lambda I squared times v is the 0 matrix. Okay, so if a minus lambda I times v equals 0, we also get that a minus lambda I squared times v equals 0. And that's how we get like this is a subset of that, which is a subset of that, which is a subset of, and so on. Okay. And because the kernels are subsets of like the increasing powers, if we just take the dimension, right, that's going to tell us that the dimension of the kernels, they're also going to be subsets of the respective increasing powers, which means that the nullities, they're also going to be increasing. Okay, so d0 is going to be less than or equal to d1, less than or equal to d2, and so on. Okay, that's just from a notion that if A is a subspace of B, then the dimension of A is going to be less than or equal to the subspace of dimension of B. Okay. And the third property is that the differences in nullities, they must not increase. Okay, so a couple of points here. Point 2 was that the nullities must not decrease, and point 3 was that the differences in nullities must not increase. Okay. Alright. Quick example here. C, let C be this 3 by 3 matrix, and find the eigenvalues of C. Okay. You can do this like a quick way, but I'm just going to compute the characteristic polynomial. Again, note that this is not the actual characteristic polynomial. It's actually going to be the determinant of lambda I minus C, but we just use C minus lambda I because that's easier to calculate and less likely to make a silly mistake in terms of like the minus signs. So the determinant of C minus lambda I is just this, which if you factorize that out, we get this thing here. Tells you that the eigenvalues are going to be 3 and 5. Okay. And okay, let's have a look at the two eigenvalues, starting with lambda is 3. Okay. So if you look at C minus 3i, you notice that we have 2 leading columns, okay, which means that the rank is 2, meaning that the nullity is 1. So let's say d of 0 is 1. Sorry, that's d of 1, my bad. D of 0 is always going to be 0, so d of 1 is going to be 1. If we take C minus 3i squared, and we reduce it down to this matrix here, notice again we have 2 leading columns, which means the rank is 2, nullity is 1. And again, C minus 3i cubed, we have 2 leading columns again, we have rank is 2, nullity is 1, this should be d2, it's d3. Okay, and all going to be 1s. And let's look at the second case where lambda is 5. Same sort of thing here, right? C minus 5i, if we reduce the matrix down, we have, again, 2 leading columns, which means rank is 2, nullity is 1. Okay. If we look at C minus 5i squared, and we reduce the matrix down, notice in this case we only have 1 leading column now, which means that the rank is 1, and hence the nullity is actually going to be 2. Okay. And same thing for C minus 5i cubed, we have 1 leading column, which means the rank is 1, nullity is 2. Okay. So for lambda is 3, the nullity at each step was 1, 1, 1. And notice that clearly obeys the theorem that the nullity should be non-decreasing and that the differences should be non-increasing. Okay. And same thing for lambda is 5. We had 1 to 2. Again, these nullities are non-decreasing and the differences are non-increasing. Okay. Notice that their nullities actually seem to terminate at some maximum value. So for lambda is 3, we just we're seemingly stopping at nullity is 1, and for lambda is 5, we're seemingly stopping at lambda is 2. And this is actually the case because the this number is actually going to equal the our eigenvalues algebraic multiplicity. Okay, so if we go back, notice that we have our characteristic polynomial here, which means that 5 has an algebraic multiplicity of 2, and 3 has an algebraic multiplicity of just 1. And that exactly equals to these terminating values here, 1 and 2. Okay? And quick lemma here, the dimension of the generalized eigenspace corresponding to eigenvalue lambda is equal to the algebraic multiplicity of lambda. Okay. So before, in chapter 6, you had the notion where the dimension of, the geometric multiplicity, which was your dimension of your eigenspace, that was less than or equal to the algebraic multiplicity. Okay. But in this chapter here, we can actually generalize the notion using generalized eigenspaces, which gets us this result that the dimension of the generalized eigenspace is exactly equal to the algebraic multiplicity. Okay. And again, this tells us that we actually only have to compute the nullity of a minus lambda I to the k up until it's equal to the algebraic multiplicity. Okay. If we compute any powers further up, so k plus 1, that's just going to result in the same nullity. Because of this theorem here. Okay. Yeah, that's what I just talked about. Geometric multiplicity is less than or equal to the algebraic multiplicity. Okay. And we're now going to get into the part where we're actually computing Jordan matrices. So we actually use Jordan chains to find the matrices P and J that we can reduce our original matrix to. So A is P, J, P inverse. For some eigenvalue lambda with algebraic multiplicity k, we need to start with some vector Vn, such that if we multiply Vn with A minus lambda I, we get Vn minus 1. Do it again, and keep doing it until we get to V1, where if we multiply this again, we get the zero vector. Okay. And in this case, what we do is we include the columns of, so we include these set of vectors into the columns of P. So one thing to be slightly careful of is that we actually start with this base eigenvector here, and we actually work our way up. Okay. Notice when we're actually computing the Jordan chains, we're starting from Vn and chaining down, but when we're writing our matrix P, we start by writing this V1, and we work our way up towards Vn. Okay, and that corresponds to one Jordan block Jn of lambda in the direct sum of Jordan matrix. Okay, so alright, and we come into the notion of block diagrams, and these are really useful into I guess giving you an understanding of like what's going on, essentially the nullities at each step, the different number of Jordan chains that can be formed, and the overall structure of your Jordan matrix. Okay. Example here. So let's say a generalized eigenspace has nullity of dimension 1 to be 5, nullity dimension 2 to be 8, nullity of dimension 3 to be 11, and nullity of dimension k to be 12, where k is bigger than or equal to 4. Okay. Now, again, we know that the nullity must terminate for some value of k. In this case, we denoted k is bigger than or equal to 4, and that's going to be like the terminating value there. Okay. How exactly we draw this block diagram, right? We start with the base case here. Nullity of a minus lambda I is 5. We just draw out 5 blocks in the base. Okay, and that's going to correspond to the eigenspace. Okay, and if we look at the nullity of a minus lambda I squared, that's going to be 8. So we have to add on 3 more Jordan blocks, and we add it on to the second layer, like this. Okay, so add on 3, and same thing. We have dimension of nullity of a minus lambda I cubed is 11. So we need to add on another 3 blocks on the third layer. Okay, and dimension of nullity of a minus lambda I to the k is going to be 12, so we need to add on 1 more block on the fourth layer. Okay, and essentially our Jordan chains now become the vertical, these vertical blocks here. So the vertical columns, that's bad drawing, so we have, that's the first Jordan chain, that's the second Jordan chain, that's the third Jordan chain, oops, here, that's the fourth, and it's going to be a fifth Jordan chain. Okay, and exactly, you want to start with a vector in this top block here and start chaining your way downwards. Okay, and again, start with the vector in this block here and then chain your way downwards. And start with the vector here and chain downwards again. And you can just start with these vectors, and if you chain down from these base vectors, you should just get the 0 vector. Okay, so chain down into the 0 vector. Alright. Okay, quick example here. So suppose A is a matrix with eigenvalue lambda, and we want to explain why the following is not possible. Okay, so these type of questions, you just want to draw the block diagram to see what's going on. So nullity to the a minus lambda I is equal to 5, so it's going to be 5 blocks in the base level. Okay. Nullity of a minus lambda I squared is 8, so we have to add on another 3 blocks in the top. Okay. Nullity of a minus lambda I cubed is 9, so we have to add on 1 more Jordan block. Nullity of a minus lambda I to the 4 is 12, so we have to add on another 3 blocks here, and for all, it's going to stay 12 for every value after. Okay. Notice that we have this sort of overhanging part over here. Let me use blue. Okay. Now, a valid Jordan block should always be like a staircase sort of Jordan block, and if we have this overhang, that's going to tell us that our whatever info we're given is not valid. Okay, and the reason why it's not valid is because if you look at the difference between these two nullities, we have 3. Difference between these two is 1, and difference between these two is again 3. Okay, and remember that our differences between the nullities should be non-increasing, right? But notice that we've increased our difference from 1 to 3, which is violating one of the rules for our nullities, right? And that's the reason why we can't have this possible case. Okay? The Jordan block is a nice visual way to see what's going on, but to explain it, you have to say that the differences in nullities can not be increasing. Okay. Okay. So let B be a 10 by 10 matrix and let lambda be an eigenvalue for B. Okay. Suppose it is known that nullity of B minus lambda is 5, nullity of this is 8, nullity of that is 9. Okay. So notice that already we have the nullity of B minus lambda I cubed is equal to 9. Right? And since we have a 10 by 10 matrix, a 10 by 10 matrix should have a total of 10 blocks in total, 10 Jordan blocks. Okay. Oh, I shouldn't say Jordan blocks, I should say blocks, because we're talking about the block diagrams. Okay. But this tells us that we can already draw out the 9 blocks from this given info. Okay. So we just have to exhaust all of the cases where the last block can be. Okay. So let's create a new page. It's a page. Yes. Okay. So we have the fact that nullity of B minus I is 5, 8, and 9. So how exactly we want to draw this out is we have the base Jordan block is going to be 5. Actually, let's first consider the cases where our Jordan blocks can be. So there's actually going to be 2 cases where this is possible. So case 1 is actually where we have just a single one eigenvalue. Okay. I should say one distinct eigenvalue. E value. Okay. If we only have one distinct eigenvalue, that's going to be our eigenvalue lambda that the question gave us, right? So if we draw out the Jordan blocks, right? So we know d of 1 was equal to 5. D of 2 was equal to 8, D of 3 was equal to 9. That was what the question gave us. So in our bottom row, we have 5 blocks here. Okay. In our next, we know that the dimension of a minus lambda I squared is 8, so we need to add on 3 more Jordan blocks. Okay. And D3 was 9, so we need to add on another block here. Okay. Case 1 is if we have one distinct eigenvalue lambda. So this is a Jordan, this is a block diagram corresponding to lambda in this case. Okay. Again, because we know that we have a 10 by 10 matrix, we need to have a total of 10 blocks in our block diagram, right? And currently we have 9, right? So the only place where we can actually place another block is actually just on top of this block over here, right? Where we have D4 is actually just equal to 10. Okay. We can't place it here, otherwise D2 would have been 9. We can't place it here, otherwise D3 would have been 10. Okay, so the only place we can put it is like over here. Right? And we can't like place it over here because D1 would be like 6. Right? So that's the only possible place for case 1. And for case 2 is actually if we have 2 distinct eigenvalues. Right? Take that mu. Oops. And the reason why we can only have either 1 or 2 distinct eigenvalues is because notice the question told us that the nullity of a minus lambda I to the 3 was equal to 9. And because the nullity of a minus lambda I cubed was equal to 9, that's going to tell us that t minus lambda has an algebraic multiplicity of at least 9. Okay, so there's going to be some other factor, so that's going to be characteristic polynomial of A, of T. There's going to be some other value, let's say mu. Okay, and again, this leads us to two cases where if mu is actually just equal to lambda, or if mu is a second eigenvalue. Okay, so if we're looking at our second case here, right? Again, the block diagram for lambda is just going to be this 5 in the bottom, 3 after that, and 1 at the top. And because we only have, in the second case, we can only have t minus lambda to the power 1, right? Our block diagram for our second eigenvalue mu is just going to be a single block in the base. Okay, that's the only way we can represent the block for mu. Right, so that's going to be the two cases where we can actually have our last block, and the question was find all the possible Jordan forms for B. Okay, so we have two different possible Jordan forms. Okay, and let's have a look at the first case here. How we actually denote the Jordan blocks is we look at the Jordan chains. Okay. So these are your Jordan chains. And using the Jordan chains, notice the first chain is length 4, so this is going to be a Jordan chain of Jordan block of size 4, corresponding to lambda, direct summed with the next chain, which is length 2. Okay. Direct sum with the next chain, which is also length 2. Okay. Direct sum with the next chain, which is length 1, J1 of lambda, and direct sum with the last chain, which is also length 1. Okay, so that's going to be your Jordan matrix for case 1. Now, oftentimes, J1 of lambda, this is just a 1 by 1 matrix of element lambda. Oftentimes, we just write this as just the lambda with brackets around. Okay, so these two guys did the same thing. Okay, and for case 2, where we have two distinct eigenvalues, again we consider the Jordan chains. So there's a chain here, chain here, chain here, chain here, chain here, and this is your last chain for mu. Okay, so your first chain is length 3 for lambda, so we write J3 of lambda. Okay, the second chain is length 2, which is also for lambda. Your third chain is also for length 2 for lambda. Fourth chain is length 1. Your fifth chain is also length 1. And this last chain here is length 1, but it's instead for the eigenvalue mu, so we denote this by J1 of mu instead. Okay, so these are your two different cases that you can have for this question here. Okay. Alrighty, moving on to the next question. Quick example here. So let C be this 3 by 3 matrix, V be 1 minus 2 minus 3. Part 1 is to calculate C minus VI V and C minus VI 5I squared V. Okay. For these kind of questions, you sort of want to expect this guy here to equal to 0. And that's going to tell you that V is going to be a generalized eigenvector. Okay. And part 2, without any matrix calculations, write down all the eigenvalues of C and their algebraic geometric multiplicities. And 3 is the lead on to find an invertible matrix P and a Jordan matrix J, such that C can be reduced to this form here. Okay. Part 1 was actually done as a previous example in example 1. So if you want to if you want a more thorough work through, just go back the recording and where we went through example 1. Okay. Part 2, well, we actually want to look at the trace of the matrix, because that's going to tell us the sum of the eigenvalues. Okay. So the trace, we just sum up the diagonal elements, 9 plus 2 plus 2, which is going to be 13. Okay. And well, in our previous work, we found that c minus 5i or squared v, this was actually the zero vector. Okay, and what this is going to tell us is that v is going to be a generalized eigenvector. Okay, which means that our characteristic polynomial for c, in this case, right, it's going to contain t minus 5, and this is going to be to the power of at least 2. Okay, there's going to be some third factor here, so t minus, just call it lambda. We don't know what this lambda is going to be. It could be 5 as well, or it could be like a different number. Okay, so that's going to tell us that the eigenvalues are going to be 5, 5, and lambda. So we can just do a quick sum of eigenvalues. 5 plus 5 plus lambda is equal to 13, telling us that lambda 3 is going to be 3. So our third eigenvalue is going to be 3. Okay. And again, for the eigenvalue of lambda 3, the algebraic multiplicity was 1, and that's going to imply that the geometric multiplicity must also equal to 1, because gm must always be bounded between 1 and the am. Okay. For the eigenvalue of 5, we know that the algebraic multiplicity is equal to 2, because we have power 2 in the characteristic polynomial. And the geometric multiplicity, well, that's going to equal to 1, because we know that if it was equal to 2, then that's going to tell us that c minus 5iv was the zero vector. Okay, in this case it wasn't. That's going to tell us that gm is equal to 1. In other words, you can also think about using the block diagram. So for the eigenvalue lambda is 5, there are two different cases we can have, which was either case 1 here, or the case 2 was if they're vertically stacked. Okay, if they're if it's part of case 1, then that's going to tell you that gm is equal to 2. Whereas for the second case, we're going to have gm is equal to 1. Okay, and because we have a chain of length 2, right? We had c minus vi times v and c minus 5i squared times v. We had a chain of length 2. We must have the second case here, where we have gm is equal to 1. All right. And part 3 was just trying to find the invertible matrix P and the Jordan matrix J. Okay, so we just want to find the eigenvector corresponding to the eigenvalue 3, and that can just be done by row reducing c minus 3i, which gets this matrix here, and we can just take the corresponding eigenvector v3 is equal to 1, 0, 2. Okay. All right. So our corresponding chains, right? So if you want to think about it using block diagrams, so for eigenvalue lambda is 5, we have this Jordan block here, and for eigenvalue lambda is 3, we have just a single block. Okay. So if we start off with our vector 1, minus 2, minus 3, we can chain it down to minus 1, 1, 1. So minus 1, 2, 1, minus 2, minus 3 is this vector here, and we're chaining it down to minus 1, 1, 1, which is in this in the bottom block there. Okay, and 1, 0, 2 is just going to be in this block here. Okay. Hence, we have A is Pj, P inverse, where J is the Jordan block, Jordan matrix. So again, if we have the Jordan block, lambda is 5, we have this vertical block, lambda is 3 is just this single block here. Okay, and well, let's use red instead because we have red in the slides. So lambda is 3, we have this. Okay. Let's use green. And again, we have we're looking at the Jordan chain. So this is one chain, this is the second chain, and the first chain corresponds to this Jordan block here, J2 of 5, and we just direct sum it with J1 of 3, which is just going to be this thing here. Okay. And for our matrix P, right? Because we wrote our J2 5 Jordan block first, okay, we have to look at the eigenvectors and the generalized eigenvectors, and we have to write those guys first, okay, before we write the eigenvector corresponding to lambda is equal to 3. Okay, and for this case here, we always start off with the base case minus 1, 1, 1, and we write it first, and then we work our way up to 1, minus 2, minus 3, and we write that vector second. Okay. Again, pretty similar in the case where we have diagonalizable matrices. The order where you write the eigenvectors is in the exact same order that you wrote the eigenvalues in your diagonal matrix. Okay, and this is the same thing for Jordan blocks. The order that you write your Jordan blocks in has to match the order that you write your eigenvectors in as well. Okay. Okay, next example here. So let A be this 3 by 3 matrix. We're given that the generalized eigenspace for the eigenvalue 2 is going to be the span of these two vectors, and the generalized eigenspace for this is going to be just span of a single eigenvector. Okay. Part 1 is to find the Jordan chain corresponding to lambda is 2 with 0, 1, 1. Okay. Now, currently for our lambda is 2. Okay. We have a span of 2 different independent vectors. Right. So that's going to be we're going to have 2 different cases that could be possible. So one is where we have this vertical block here, and the second case is that we have a horizontal 2 blocks. Okay, and for the case where we have lambda is 3, that's just going to be a single block here because we just have one independent eigenvector. Okay, and question 1 would actually allow us to find which 2 cases lambda is equals to is, whether we have the 2 vertical blocks or we have the 2 horizontal blocks. Okay, so and if we actually do the calculations, right, we have to start with 0, 1, 1, chain it down to minus 1, minus 3, minus 2, and we chain it down again to 0, 0, 0. So this is going to be chain of length 2, right? Okay, and that's going to tell us that the only possible case is going to be this first case here where we have this vertical block, because this is the only case where we have a chain of length 2. Notice that the second case we have just single chains here with chain of length 1. Okay, so that's going to tell us what the Jordan blocks are actually going to look like. Okay, without any calculations, write down the geometric multiplicity of lambda is 2. Again, from our work in part 1, we figured out that the block diagram must look like this, and that's going to tell us that the geometric multiplicity, and again, if you're given a block diagram, the geometric multiplicity is just going to be the number of blocks in the base, in the bottom row. So in this case, we just have 1 in this case, right? So again, geometric multiplicity can't be 2, right? That's the second case here where we have 2 blocks in the bottom row, and that's because we have a chain of length 2, right? So that's going to tell us that GM is going to equal to 1. Okay, and again, we do the same thing where we start off. So we had a Jordan block like this. This is corresponding to lambda is equal to 2, and this other block is lambda equals to 3. Okay, again, we can write the Jordan matrix as the direct sum of J2 of 2 with J1 of 3. Okay, there we go. Because that's going to be your first chain, and that's going to be your second chain, and that's exactly what they did here. This is your J2 of 2, and this is a J1 of 3. You just pad it out with zeros. Okay, And again, you have to match your, okay, let's use red in this case. You have to match whatever order you put your Jordan blocks around, you have to match the eigenvectors in as well, right? So for the first case, we have J2 of 2. We start off with the eigenvector, and we work our way up. Okay, so we start off with this -1, -3, -2. We write that in our first column. Then we work our way up towards 0, 1, 1, and we write that in the second column. And the third column is just going to be the eigenvector corresponding to 1, 4, 2. Okay. All right. And question 4, find a vector v in GE of 2 and a vector w in GE of 3 such that v plus w is 2, 1, 0. Okay. Okay, so if we go back, well, if we look at what GE of 3 is, that's a span of these two vectors. So all we're trying to do here, we're just going to solve 0, 1, 1, and GE of 3 was a span of 1, 4, 2. We're just going to solve this augmented matrix here and find what the constants are in front. Okay, so I'm not going to go through this last example. You're just solving this augmented matrix equation here. If you're good, you can sort of inspect out what the constants are from each eigenspace. Okay. Okay, now, next theorem is that the direct sum of the generalized eigenspaces of any matrix A is actually going to span out the set of complex numbers. Okay. And a quick remark on finding Jordan chains is that the question, they're not going to always tell us what vector to start with. Okay. Sometimes you're gonna have to start. You're gonna have to like cook up your own vector in your Jordan chain. Okay, so example in the 2021 finals, as part of the working out, they were expected to cook up their own initial vector given the following details. Okay, so there is a Jordan chain of length 2 for the eigenvalue 2 for the following matrix A. Okay, what this is going to tell us is that A minus 2i is going to be this matrix here, and you need to find some vector v2 such that if you multiply a minus v2, that's going to equal to v1, and if you multiply a minus 2i with v1, that's going to equal to 0, where v1 is actually non-zero, right? Because if v1 is 0, the chain has ended early, and we just get a chain of length 1, right? Okay, so the thing that you want to spot here is that okay, we have a minus 2i is this. Let me just rewrite this here. 0, 0, minus 1, 2. The thing you want to spot is that the second column is actually all zeros, right? So if we multiply this matrix by the vector 0, 1, 0, 0, that is going to just extract out the second column. And that's just going to turn out to be the 0 vector. Okay. So if we have v1 to equal, so if we suppose v1 is equal to 0, 1, 0, 0, we essentially need to find a vector v2 such that if we multiply a minus 2i with v2, we get this vector here. Okay. Okay, let me open a new page. Add pages, new page. Okay, here we go. So we have a minus 2i is equal to, oops, a minus 2i is equal to 0, 1, 1, 0, 0, 0, 0, 0. Oh, that should be a 1. So ink, that should be a 1. 0, 0, 0, 1. 0, 0, minus 1, 2. Okay. And we want, if we multiply by some vector v2, so say a, b, c, d, we want this to equal to v1, which is 0, 1, 0, 0. Okay. And we sort of have to just inspect this out, right? Now, why is this disappearing? So it should be 0 here. Okay. We can just sort of compare each component and see what goes on. Okay. So if we want to get out the first component 0, right? How we actually get out the first component is we multiply this first row in the matrix by the vector here. But notice that the first row is just 0, 0, 0, 0. So 0 times a plus 0 times b plus 0 times c plus 0 times d is going to be 0 for any numbers a, b, c, d. So that's not really useful, right? So let's look at the second row. If we look at the second row, we have 1, right? And how we get the second row is we multiply this second row here by the vector a, b, c, d, right? And that's going to actually get us that, so 1 times a plus 0 times b plus 0 times c plus 0 times d, that's just going to be a. And that must equal to our number 1. Okay? So that immediately gets us that the number a is equal to 1, right? So do the same thing. If we look at the third row, we have a 0, and to get the third row, we multiply the third row of the matrix with this vector. So 1 times a plus 0 times b plus 0 times c minus 1 times d, which gets us a minus d is equal to 0. We know that a is 1, meaning that d must also equal to 1. Okay, and we do the same thing for the last row here. So to get the last row, we multiply the last row of the matrix by the vector a, b, c, d. Okay, so we get 0 times a plus 0 times b plus 1 times c plus 2 times d is equal to 0. Okay, so we have c plus 2d is equal to 0, meaning that we know that d is 1, so c is minus 2. Okay. Okay, that's going to tell us that our vector v2 is going to equal to 1b, what is c, minus 2, and 1. And b, we can actually just let it be any number. It doesn't actually matter because it has no effect on our last result. So just let b to equal like 0. So we choose v2 to be this this vector here, meaning that a minus 2i times v2 is actually going to equal to our 0, 1, 0, 0, which if we call v1. And we know that from our previous work that a minus 2i times v1, that's going to be the 0 vector. Okay, so that's how you sort of cook up your own vector of length 2, such that if you chain it down, we get v1, and chain v1, we get the 0 vector. Okay. And that brings us on to the next part on the Cayley-Hamilton theorem. So for any matrix A, if we take the characteristic polynomial of A and we plug in A itself, that's just going to return our 0. Okay. So a quick example here. Let V be a finite dimensional vector space and T just be a linear transformation that goes from V to V. Right? And suppose the characteristic polynomial of T is given by this cubic equation here. Okay. Now, suppose V is in the image of T squared minus 4T plus 6I, and it's also non-zero. Right? And it tells us that using the Cayley-Hamilton theorem, prove that V is an eigenvector of T with eigenvalue 1. Okay. So ultimately, what we have to prove is that we have to prove that T of V is equal to 1 times V. Okay, that's the definition of like an eigenvector with eigenvalue 1, and we know that eigenvectors must be non-zero. Right? So this can't be the 0 vector, but we already know that we suppose V is non-zero. Right? So we don't have to check that V is non-zero because the question already gave us that. Okay, so we just have to prove that T of V is equal to 1 times V. Okay. yeah, we're just trying to show that T of V is 1b. And again, by the Cayley-Hamilton theorem, we know that CP, the characteristic polynomial, if we plug in T into it, we should get the zero element, zero matrix, right? And if we chuck these guys over to the other side, so this guy, chuck it over to the other side, we get this equation here, right? Now, the question has also given us that V is in the image of t squared minus 4t plus 6i. And this, by definition, tells us that V is going to be t squared of u minus 4t of u plus 6u for some u in V. Okay, that's the definition of an image. And notice that we are trying to prove that T of V is equal to 1 times V. Okay, so what this is going to tell you is that we sort of just want to apply T to both sides and see what happens. Okay, that's, sorry for the crammed writing of here, but we want to apply T to both sides and just do some manipulation there. Okay. So we have T of V is going to equal to, or it's just going to be T cubed of u minus T squared of u plus 6T of u. And notice that T cubed means we apply T 3 times, and T squared means that we apply T 2 times. Okay. But by the Cayley-Hamilton theorem, we know that T cubed is equal to 5t squared minus 10t plus 6i. Right? So we can replace this t cubed with 5t squared minus 10t plus 6u. And if we simplify this expression down, we get t squared u minus 4tu plus 6u. Okay, which was v from our definition. Okay, so T of V is equal to V, and we know that V is non-zero from the question, telling us that V is an eigenvector corresponding to an eigenvalue of 1. Okay, that was a quick example using the Cayley-Hamilton theorem. Alright, now we get onto the final topic on matrix exponentials. Right? The first thing we look at is the definition of an exponential of a matrix. Right? So suppose we have a square matrix A is an n by n, then the exponential of A is defined as e to the power A, and we actually use the power series definition of exponential to define the exponential of matrices. So this infinite sum here. Okay. A couple of useful properties, right? If A and B commute, so that is if AB is equal to BA, then we can actually write x of A plus B is x of A, x of B. Right? That's your pretty intuitive. So e to the A plus B, that's going to equal to e to the A, e to the B. Right? And for like real numbers, so for like complex numbers A and B, you've actually just been using this property all along, and that's because we know that complex numbers, they commute easily, right? You can just swap them around. But when it comes to the matrices, they don't normally commute, so we need the property that they must commute for us to use this property here. Okay. Inverse of x of A is just x of minus A. That is again very intuitive. If we have e to some number A, invert it, that's just going to be e to the minus A. Okay. And the third one is also very intuitive. If we take the derivative of x of ta, you can sort of imagine this as chain rule. We take the A and we multiply out front as well, and we can multiply either way, to the left or the right. They're both the same. Okay. Again, d of dt, if we look at it in the e form, so e to the ta, that's just going to be e to the ta times chain rule. We have a, or we can just chuck that on the left as well. It doesn't matter, right? Another couple of useful properties, right? So if we have A is similar to B, so A is P, B, P inverse, then we can write x of A is equal to P times x of B times P inverse. Okay. This can be proved using the power series definition. Okay. And another useful property is if A is a direct sum of n different matrices, then x of A is also going to be the direct sum of x of those n matrices. Okay. And one of the more commonly used is if we look at the exp of a Jordan block, so multiplied by t. Okay, that is actually going to be this this whole matrix here. Okay, and what you want to notice is that we firstly have e to the lambda t out front, and along the diagonals we have a bunch of 1s. Along the super diagonals we have a bunch of t's, and we above that we have t squared on 2 factorial, and we keep going until we get to t to the k minus 1 over k minus 1 factorial. Okay, so notice that these are actually the exponential series of e to the t. Remember that e to the t is 1 plus t squared on 2 plus and so on, right? This was very similar to when we were calculating the powers of Jordan matrices, right? Instead we had the binomial coefficients. In this case we actually have the exponential terms 1, t squared on 2 factorial, all the way until we get to t to the k minus 1 on k minus 1 factorial. Okay, and the quick sort of proof is that we can express again t of j k of lambda as Jordan form, the Jordan block t j k of lambda. We can write it as lambda times the identity matrix k by k plus the ones on the super diagonal. We'll just call it nk. And if we take the exp of this, we can actually have these guys commute. So exp of t lambda I k plus nk. Okay, and we can actually break this up into 2 different exponentials, and the reason is because lambda ik actually commutes with nk because the identity matrix commutes with like every matrix, right? So this actually just exp of t lambda ik times exp of t nk. Okay, and this guy here turns into this number here, and well, it's not a number, it's actually this number multiplied by the identity matrix, but we just, when we multiply this identity with this whole matrix, that just disappears, right? And this guy here corresponds to this huge function there, right? Alright, so quick example, if we want to take the exponential of t times the Jordan block of 5 by 5 with 2, well, again, we have the e to the 2t out front. We write the 1s on the diagonal, t's on the super diagonal, t squared on 2 factorial on next, t cubed on 3 factorial, and t to the 4 on 4 factorial. Okay, and we keep filling it up until we hit our size. Okay. Okay. Quick example here. So suppose we have this matrix C 3 by 3, and we want to find the exponential of TC. Right. Previously we had that P was this matrix here, and the Jordan form was this here. Okay. We know that we can write C as P J P inverse, and from one of our lemmas previously, well, we have TC is going to equal to P Tj of P inverse, and from one of our lemmas, if we take the exponential of TC, we can just chuck this into the exponential of Tj directly. Okay, and we get this. Right? So to calculate the exponential of TC, we just need to calculate the exponential of this Jordan block here. And again, we have exponential of Tj, Now this Jordan matrix is a direct sum of Jordan blocks. Right? So we have direct sum of j to 5 with tj1 of 3. And remember that the exponential of a direct sum is the direct sum of exponentials. So we can actually break this up. So direct sum with exp of j1 of 3. Okay. And it is these guys individually that you can actually calculate from using our previous work that we've done, like over here, like this stuff, right? These individual guys we can actually calculate. Right? Yeah, that's what we did previously. So again, the direct sum of individual exponentials, and that would get us this first expression here, direct sum with this next expression, right? Alright, and if we put these two matrices together, we get these guys connected diagonally, and we pad the rest out with zeros. Okay. And hence exp of TC is going to be P times this matrix times P inverse, right? And if the question asks you to calculate the final matrix, you're going to have to find the inverse of P, which is generally not going to be nice, and then you're going to have to like multiply by P and then multiply by P inverse, which is generally going to be quite tedious, right? But the computation, you know how to do the computation, it's just a bit tedious. Okay. Okay, now this brings us on to the next theorem, called the column method. So if we have a Jordan chain, right, we're starting off with V1, and we chain it down to V2, chain it down to V3, and it keeps going until we chain it down to Vk. Right? Then if we have exponential of t a and we multiply that by V1, we actually can write it in this form over here. Okay, and that's to emphasize if we chain this down one more time, so a minus lambda I, that brings us onto the zero vector. Okay, and the quick proof for this is that if we have exp of ta, we can write this as exp of t times lambda I plus a minus lambda I. Okay. The reason why we want to write this in a minus lambda I because we want to make use of this thing here. We chain it down, and this is going to be that should be I. We multiply by v1. Okay. That's going to equal to exp of t lambda I plus t of a minus lambda I v1. And we know that the identity matrix that commutes, so we can actually break this up into exp of this guy here, like that, right? And then this first guy here would correspond to this expression here, and this second guy here, that would correspond to this larger chunk over here, right? And what we do is we simply rewrite this second exponential in power series form, and we multiply it by v1 and use this property here that we keep chaining it down to get our final expression like that. Okay. Alright, now we look at matrix exponentials for mainly one reason, essentially, and that's to solve systems of differential equations, right? We can actually compute exp of ta times v for some vector v without actually having to compute the exponential matrix exp of ta. And that's really useful because computing this matrix e to the ta is generally really tedious, especially for like 3x3 and large matrices, and that's because you're going to have to find the Jordan form of your matrix A. You have to compute the exponential of your Jordan matrix, which is usually going to be a direct sum of your Jordan blocks. You're going to have to find the matrix P, you're going to have to invert P, and you're going to have to multiply three matrices together back, which is sounds like really tedious, right? And we can actually compute exp of TAV without like finding this huge thing, which is going to save us a lot of time. And so looking at this theorem here, so the solution to dy or dt is equal to the matrix A times y with initial condition y0 to c is actually going to be in this form here. Y is the exponential of ta times c. Okay. And that allows us to find what this solution is without finding x of ta. Okay, so suppose I have a C, this 3 by 3 matrix, V is 1 minus 2 minus 3. We're given that V has a chain that if we chain it down, we get minus 1, 1, 1, and chain it again, we get the 0 vector. And we want to use this to solve the initial value problem y dash is cy, where y of 0 is just V. Okay. Now, we know that the solution is in the form of x of ta multiplied by the initial condition 1 minus 2, 3. Right? And using our columns method, right, we can actually just easily calculate this as e to the 5t times this first vector 1 minus 2 minus 3 plus t times this second vector that's being chained minus 1, 1, 1. Okay? And that is going to equal to e to the 5t multiplied by this. Right? And this allows us to calculate solutions of differential equations without actually finding the exponential. Right? And this column method was just using this theorem here. Okay. Okay. Moving on to the next example, find a particular solution to this inhomogeneous differential equation, y dash is cy plus this t e to the 5t times w, right? Where c is, again, this matrix, and w is this vector here. Okay? And we're given that w is a generalized eigenvector of c. Okay. The general solution, sorry, the general technique of solving these guys is we sub y is e to the tc times a function z in terms of t, okay, into the differential equation, right? And notice that if we sub this in, the left-hand side becomes, if we differentiate our y, we get this, and we equate it with the right-hand side. Notice that these guys cancel, and if we chuck this guy over to the other side, we get z dash is this expression here, okay? And we have to solve for what z is essentially, okay? But firstly, we have to solve what e to the minus tc times w is, and again, we're not actually going to find the exponential e to the minus tc. We're just going to do some tricks that allows us to find e to the minus tc times w, okay? So again, we're given that w is a generalized eigenvector, so if we chain it down, so c minus 5i, we get this. When we multiply it again, we get the 0 vector. Okay. And that's going to tell you that using our columns method, if we multiply e to the tc with w, we get this expression here. Okay. But notice that we wanted to find e to the minus tc multiplied by w. Right now we have e to the tc times w. And we can just easily solve this by replacing every instance of t with minus t. Okay, and that gets us e to the minus 5t, and we replace minus t over here. Okay. Okay. Therefore, we found that e to the minus tc times w is this expression here. So if we re-plug it into that expression into here, we get this expression here. Right. So z dash t is equal to this guy here, and we just want to integrate to get our expression for z. Right. Integrate with respect to t. And obviously there's going to be some constant of integration c, and the question is, how do we deal with this constant of integration? Right. Now, usually in initial value problems, you're given what the initial condition is, and in that case, you know that the initial condition y0, where we sub in t0, is going to be e to the 0a times z0, which just becomes z0. Right? So whatever your initial condition that the question gave you, you can just replace it with z0. Right? So if we sub in t is 0, we just get c is the initial condition. Right? But in this case, they didn't give us any initial conditions, so we're just going to proceed as usual. Right? Remember that our original solution was y of p is equal to e to the tc times z of t. Right? We know what z is. Right? We know that we found z is this expression here. So we just multiply that out like this. Right? And essentially our last step is to find what these guys are. Okay. And again, we found the Jordan chain that -8 to -4 chains down to -6, and this chains down to 0, 0, 0. Right? So that's going to tell us that this first guy here, using our columns method, we get this expression here. And again, this second expression, again using our columns method, that's going to get this expression here, right? And then if we combine everything into one single nice expression, we get this expression over here, okay? And that's going to be our solution to this next example, okay? And that is going to be it for today's seminar, and that's going to be it for the Math2601 seminars for this year. If you have any feedback, can you please scan this QR code? Any feedback would be really useful in helping us improve for next year. But in other words, that is it for today, and good luck with your exams for uni. See you guys around.